All right, we've got some 17C examples of finding and classifying critical points for functions of two variables. So here we have a function f of xy equal to 4 over x plus 2 over y plus xy, which I've also thought of as 4 times x to the negative first and 2 times y to the negative first. The partial with respect to x is negative 4x to the negative second plus y, set that equal to 0. And what we're going to do with that is we're going to solve for one of the variables. So it makes sense to say, okay, that's going to give us y equal to positive 4 over x to the negative second, or 4 over x squared. Similarly here we get the partial with respect to y is the derivative with respect to y, so negative 2y to the negative second plus x. Solving for x, we get x equal to positive 2 over y squared. And we're gonna work with these to find the critical points. Also, we have our second partials. Our fxx is the derivative of this with respect to x, so it's positive 8x to the negative third. Our fyy is positive 4y to the negative third. And our fxy is just 1, our fyx is just 1. So we use these to solve for critical points. So we need y to equal 4 over x squared and x to equal 2 over y squared. So I'm going to tell you what the answer is before we actually get there. The only critical point here is actually, where'd it go? I forgot what it was, it's alright. I think it was x equal to 2 and y equal to 1. Because if x is 2, you get 4 over 4, which is 1. And if y is 1, you get 2 over 1, which is 2. But we have to put these together to solve for this. So the way we do that is I'm going to take this, x equal to 2 over y squared, and substitute it in for x there. So let's see, I'm going to get y equal to 4 over 2 over y squared squared. So that's going to be y equal to 4 over y to the fourth. Flip and multiply, or flip and multiply, sure. Y equals 4 times y to the fourth over 4, cancel. Y equals y to the fourth. The only solutions are 0 and 1. The way I would solve this is by actually subtracting y from both sides. So I'm going to do it over here. 0 equals y to the fourth minus y, and then you can factor out y and get y times y cubed minus 1. So the solutions are y equal to 0 and y equal to 1. Looking back here, if y equals 1, x equals 2. So y equals 1, x equals 2. And if y equals 0, you don't get anything because 2 divided by 0 is undefined. So that actually is impossible. So sometimes something that seems like it's going to be a critical value actually isn't. So if y was equal to 0, we wouldn't get a critical point, right? Looking back to the original function, it's undefined at 0, so it makes sense that y equals 0 doesn't give us a critical point. Okay, so now that we found the one critical point, so our critical point is x equal to 2, y equal to 1. Then we're going to evaluate the determinant of the Hessian, fxx fyy minus fxy squared. So fxx fyy minus fxy squared, right, that's our capital D. That's going to equal, so fxx is 8 over x cubed, fyy is 4 over y cubed, and fxy is 1. So plugging in 2 for x and 1 for y, so the determinant of the Hessian evaluated it to 1, we get, sorry, the equal sign is terrible. We get 8 over 8 times 4 over 1 minus 1, so that's 4 minus 1, which is 3, which is positive. And when the determinant of the Hessian is positive, it means we have, what's the word I'm looking for? It means we have a max or a min. And so to determine it, we have to look at either fxx or fyy, and we see that when this is positive, they're both the same. In this case, fxx is positive as well, fyy is positive, right? Plugging in 2, 1, 2 for x gives you a positive 1. You get 8 over 2 cubed, which is 1. And fyy is also positive. In a different problem, you could also get them both being negative, and that would give you something different. But here, since both the second derivatives are positive, it means we're concave up, which means we have a minimum. So a minimum at the critical point 2, 1. Okay, I'm going to do